All right. Describe the influence the student who is assigned to practice the following steps to solve a Rubik's Cube 14 times has on the equation of the least squares regression line. Where is that particular student's dot? This guy right here, right? So here's 14. So yesterday we looked at, you guys played around with scatter plots and adding these points and seeing how it would affect it. How would a point being added up there affect my least squares regression line? What's it going to do to it? It's going to shift it up because it's also really far out here. What else is it going to do to it? Would it tip the line at all? Yeah, remember the horizontal ones changed our slope. If I have a point out here, let's pretend for just a moment that that's my least squares regression line without this point. When I add that point in, what would we see happen to this? It's going to tilt up. It's going to pull my line up towards that point. So if it's going to tilt up like that, how is it affecting the slope? How would it affect the slope of this particular line? Yeah, it's going to make it less negative, right? It's going to make it shallower. Technically, because this is negative slope, if I pull it up, if I make it less steep, we would say that that is a slope increase. It's going to make the slope less negative. When I add a point that is above my least squares regression line, it's going to increase my slope. Sorry, when it's over on the right like this, and I add a point above. If I add a point below, it's going to pull it down so it would decrease my slope. If it tilts my line up, so my line becomes less shallow, what's going to happen to the y-intercept? That's going to decrease because it's going to pivot like this. My line would tilt like this. So my y-intercept will decrease. All right, let's go look at the next part. Part B. Describe the influence the student who was assigned to practice the following steps to solve a Rubik's Cube 14 times has on the standard deviation of the residuals, that's S, and on R squared. Talk to me about the size of this residual versus the size of, say, this residual. What would the size of this residual be in comparison to this one? It's a lot larger, right? So if I'm finding the standard deviation of the residuals with this point in there, would you expect it to be higher or lower than if that point wasn't there? It'd be lower without that point, right? With that point, that has a very large residual, so the standard deviations of the residuals would be really high. So adding this point in is going to increase our S. This will increase. What about for r squared? What does r squared describe again? Yes. How much of the difference, the variation in our y variable is because of changes in our x variable? Sorry, that zoomed way in. There we go, that's better. So how much of the time in minutes is attributed to the number of practices as represented by this least squares regression line? Without that point, what do you think? Does that look like a reasonably strong association or no? Yeah. With that point, is it as strong? No. So what's it going to do to my r squared? Decreases it. Looking at our third question here. It says the mean and standard deviation of the number of practices are x bar is 8 practices. The standard deviation of our x's is 4.47 practices. The mean and standard deviation of time are y bar equals 7.71 minutes. And the standard deviation of y is 1.20 minutes. The correlation between the number of practices and the time to solve the Rubik's Cube is r equals negative 0.793. Find the equation of the least squares regression line for predicting time to solve the Rubik's Cube from the number of practices. So my equation is going to be time hat, because that's my y variable, equals a, that's my y-intercept, plus b, there's my slope, multiplied by the number of practices. That looks like a squared on the A, and it's not. It's just supposed to be an arrow. If you look up in the box labeled important ideas, over on the far right, there's some useful equations that we need to use here. What are we going to use to figure out what A is? How do we figure out what A is? Y bar, or the mean of y, minus b times x bar, or the mean of x. Do we know what y bar is? 7.71. Do we know what b is? Nope. Do we know what x bar is? What is x bar? 8. Do I have all the information I need in order to be able to find A? I need to know what the slope is. I need to know what B is to be able to plug in so that I can find my y-intercept. So I have to kind of put this on pause for just a moment. How do we find the slope? Yes, B is equal to R times the standard deviation of y over the standard deviation of x. Do we have a value for R? Yes, what is R? Negative 0.793. Do we have values for Sx and Sy? What is Sy? Because that goes on top. 1.2. And what is Sx? 4.47. I want you to calculate that for me now so that we have our value for B, our value for the slope. Negative 0.213. So here's our slope. Now I can use that information and put it over here in the place of B. Negative 0.213 times 8. Use that to find A. So I have 7.71 minus negative 0.213 times 8. $9.414. So now I have my y-intercept. I have my slope. Do I have enough information to be able to write the equation of the least squares regression line? Yes. So let's go ahead and fill that in. We're going to write that in context. So I'm going to have time hat equals 9.414 plus or minus on this next piece. Minus, why minus? Slope was negative. Hold on, that didn't all catch. Scoot all of this over so that I have enough room for this guy. So minus 0.213 times the number of practices. Will you need to know how to calculate the slope and the y-intercept? Yes. Those are formulas that you will need to know how to use. To find the slope, it's the correlation coefficient R times Sy over Sx. So similar to just what slope means, rise over run, y over x, only it's Sy over Sx times our correlation coefficient. To find A, y bar minus the slope times x bar. All right. I want you guys to flip forward a couple pages. We're going to go to page 21. I really wanted to be able to do this today, but we're kind of running short on time. So I'm going to talk to you about a simulation that was done with pullback cars. Did you guys ever play with cars when you were a kid that, like, you set it on the ground, you pull it back towards you, and then you let it go and the car takes off? Does anybody know what I'm talking about? Yeah. They have like these little springs in them and gears so that when you pull it back, it like saves up that energy, and then you let it go and it takes off in the opposite direction. So with these pullback cars, testing this out at pulling it back 2 inches, pulling it back 4 inches, pulling it back 6 inches, pulling it back 8 inches, doing 3 trials of each. these were the results that I got from that. For the most part, that relationship seems to be showing me that as you pull it back more, it travels farther, right? So as pullback distance increases, the distance that it's traveling increases. We're going to talk about 3 different regression models here, and we're going to create scatter plots for those and calculate the least squares regression line. So for the first one, we're just going to do a linear plot. So on my x-axis, I just have x. On the y-axis, I have y. Comes out looking like this. Here's my scatter plot. I just used Stapplet to create this. We had 3 trials at pullback of 2 inches. We had 3 trials at a pullback of 4 inches. 3 trials at 6 and 3 trials at 8. That's why my dots are kind of stacked on top of each other here. Sketch this into the spot where you've got the linear plot, the XY plot. The R value for the least squares regression was 0.939. What does that tell you about this relationship? If it has an R value of 0.939. It has a strong positive linear relationship, yes. Strong positive linear relationship. Our R squared is 0.882. So 88% of the variation that we see in distance traveled is because of this linear relationship with the pullback distance. And here was the equation of the least squares regression line. Go ahead and copy all of this down into that space where you have the linear model. What do you notice as you're copying this down about the residual plot? I'm curious what you notice about the residual plot. What did you say? Looks kind of like a parabola. Starts high, goes low, and comes back up. What did we say the other day that meant about this? That it's not that it's not got a linear pattern to it. I can see it has a linear-ish pattern to it. It certainly has a very strong R value, but is a linear model the best model for it? No. There's this leftover curved pattern. Linear model is not the best fit. We skipped some pages. We're on page 21 right now. If you need to, snap a quick picture of this so that you can continue copying it down in your notes. But I want to put up the next one, the quadratic plot. Do you need to snap a picture? Okay. When I put this same information into Staplet and I asked it to do a quadratic plot for me, this is what I got. I want you guys to sketch this down into your notes for the quadratic plot. Now, on the x-axis, I don't have 2, 4, 6, and 8. My dots are at 4, 16, 36, and 64. We've squared all of those x's. What's our R value this time? It's stronger. The R value got stronger. What happened to the R squared value? It got quite a bit stronger. So now distance traveled hat is equal to 1.4806 plus 0.57009 times the pullback distance squared. What do you think about our residual plot here? Do we have a leftover pattern in our residual plot here? I still see this kind of curved shape to the residual plot. Still has a curved pattern. This is not just random scatter. Not the best model. Does this residual plot look more curved or less curved? Like, is there more of a pattern or less of a pattern than the linear one? There's less of a pattern, but there's still a pattern there. My R value is higher, my R squared value is higher, so this is a better model than my linear model. But because I still see that leftover pattern in my residuals, this is not the best model. Snap a picture if you need to. Because then I want to put up this last one. So everybody had a chance to snap a picture if you need one? All right. This last model is what kind of a plot? An exponential plot. For my exponential plot, I have x and then the log of y. This one by far has the most linear appearance. Look at my R and my R squared. That's the highest R out of all three of them, right? Certainly the highest R squared out of all three of them. Is there still a really strong curved pattern to our residual plot? No. No leftover pattern. So this one is the best model for us. Here's the equation for our best model. The log of distance traveled hat, because it's log of y, is equal to 0.4162 plus 0.1464 multiplied by the pullback distance. Snap a picture if you need to. I want to answer these two questions that are down at the bottom of the page. Does anybody still need to get a picture? Which regression is the best choice for the data? Exponential. This one has the highest R squared. And no leftover pattern in the residual plot. I want you guys now to calculate how many inches you would have to pull back for a finish line of 80 inches. So we're going to use our best model. The best model was log of distance traveled is equal to what? What was that equation? Oh, 0.462? Got it. Sorry. 0.4162. My apologies. Times the pullback distance. So what are we going to sub in if we're going to calculate how many inches we'd have to pull it back for a finish line of 80 inches? Where do I make my substitution? Distance traveled, we're going to replace with an 80. So we're going to have log of 80. This is just common log, so that's a log base 10, which is on your calculator. So I want you to work backwards and solve. Let's figure out approximately what the pullback distance would need to be. Leave everything on your calculator and just use that answer key if you need to, so that we keep it exact until the very end. Anybody have it calculated out? Yes, Amy. 10.156. Would we need units with that? Yes. What should our units be? Inches. All right. So flip it over on the back. A couple minutes left. Big idea for today. Choosing the best regression model. We're going to check the scatter plot for a linear pattern. We're going to check the residual plot for no leftover pattern. Check that for r squared, or check for the r squared that is closest to, it can't be -1. Scratch that out. Since it's squared, it's always going to come out positive. You want the r squared that is closest to +1. So that's how we find our best regression model. Looking at these three models down in the check your understanding section, which of these three models, just based on the scatter plot and the residual plot, seems like it would be the best model? C. Why? I like it. Yeah, there's no curve. This is the one that looks the most like random scatter, not a pattern. What do you notice about the scatter plot itself? Which one looks the most linear? C looks the most linear. So C would be the best here. The scatter plot is most linear. And the residual plot has no leftover pattern. Number one, we don't really have time to do this, but what is it asking you to do? To sub in. 80,000 would go in the place of what? Income. For these last two, after you simplify this side over here, you have to do e to that power, because that's how you undo a natural log. The 3.3 homework is due on Tuesday, so if you guys still have any questions about it on Monday, please start looking at it. It's not a very long homework. Start looking at that. Come in with questions on Monday. Monday, what we're going to do is we are going to start off by going over those FRQs that you guys did on Wednesday. We're going to kind of debrief that at the beginning of class. And then after that, well, we can't jump Barbie on Monday or Tuesday because PPAC is like occupied. I'm still trying to find a time to get us in there. So I'm going to have you guys get back into your original groups, and using what you know now from this module, from this chapter, we're going to try to find the best model and then predict how many rubber bands you would need to give Barbie the most exciting yet safe bungee jump she could have off the balcony there, which is 18.5 feet.